And of course, we save the best for last, like always. I'm glad you've all stayed. I was told that there's a co-presenter also, Rohit, will also be presenting with you as well. So our next presenter is Dr. Vivek Bedekar. He works as the senior scientist for Papadopulos and Associates. He has developed numerous modeling codes and is the lead author of MT3D USGS. Would you welcome him?
Thanks, Paul. Can you all hear me? Okay, great. Fantastic session, Paul. Data, more data. I don't think we can overstate the importance of data. Kelly presented how to visualize that, how to communicate with data. That was fantastic. Chuck, your tool was great. I think I have a bunch of questions for you, which we can talk about later. So thanks for presenting that. The aspect we are presenting in this talk is to bring another, in my opinion, quite underutilized data, which is aquifer parameters. And we'll be talking about aquifer parameters in the context of their use in modeling and model development and model calibration. So with that, in that context, we believe aquifer parameters are quite underutilized, and to a couple of reasons. One is sometimes that information is not available, and at other times information is available, but how do you utilize that information and synthesize that within a modeling framework? And so in some ways, to bridge that gap, this tool that we will be talking about, Texture2Par, that kind of bridges that gap. So in that context, that's the premise of our talk. So I know I'm in between you and the beer that's waiting outside, so I'll be brief. If I run through quickly and something's unclear, come catch me. I'll be there. So, feel free. There's a couple of equations in there which will help you relax, but just bear with those, and we'll go through this together. This is the project team. My colleagues at Papadopulos and Associates, Tim Durbin, and our colleagues, the prime contractor, Woodard and Curran. And we did this project for California Department of Water Resources, but we've applied this model and this tool in other areas that we will see as an example. The overall outline, we'll look at what this tool Texture2Par does, what it is about, how it is used. And we'll look at a couple of examples in California and in Arizona. We'll discuss Texture2Par version 2, what we are doing now, specifically to integrate airborne electromagnetic surveys, geophysical data that those surveys generate, and how do we get those into the model and convert those numbers to aquifer parameters for model development and calibration. And then Rohit will talk about the applications in Texas, and then we'll close. Okay, so what is Texture2Par? It is a pre-processing utility program that basically looks at sediment texture data from bore and well and boring logs, takes that, calculates and estimates aquifer parameters, creates text files needed for a numerical model that will eventually, those numerical models will be used for groundwater management and decision-making systems. So in concept, that's what Texture2Par does. How does it work? It reads model grid. It reads location of well logs. It interpolates well log information, and specifically it looks at the sediment texture data. Okay, what percent coarse there is, how many percent fine material there are, and it integrates that onto the model node itself. And you have an end member value, for example, and applies a power law averaging. And let's look at what this power law averaging does. In here, if essentially you know at each model node after interpolation, you know what percent coarse value there is, how many percent fines, which is 1 minus your percent coarse. You have end member values. For example, here, if we are calculating hydraulic conductivity, right? What is your hydraulic conductivity for a coarse-grained material on an aquifer scale? What is your hydraulic conductivity for a fine-grained material on an aquifer scale? You average those two, and it's not a straight arithmetic average. It's something called power law averaging, and we'll talk about that in the next slide, why this is important. So this P is another term that comes in. It all goes into that calculation, and you get a bulk parameter value at a model scale. This could be hydraulic conductivity, horizontal or vertical. It could be specific storage. It could be specific yield. All these aquifer parameters that go into a model. And then you can use those to calibrate your model and refine. Okay, so talking about power mean exponent. When you use this exponent P and you set that value close to 1, for example, the equation becomes arithmetic averaging, okay? When your exponent is close to 0, when it tends to 0, it should be 0, it's a typo, it acts like a geometric mean. And when the parameter P is set close to -1, a negative value, it acts like harmonic mean. So when calculating horizontal conductivities, typically values close to 1 are used. And when calculating vertical hydraulic conductivities, a negative value is used, which creates lower conductivity values because it's using harmonic mean. But what's more interesting is the shape of these two, okay? So when you look at horizontal conductivity varying by x-axis is your percent coarse, it takes a different shape versus when you look at vertical conductivities using harmonic averaging, it takes a different shape. Why is that important? The importance of that is even if you're using coarse-grained anisotropy to 10, that you're saying, okay, your horizontal is 10 times more than vertical, okay? And for fine-grained, it's the same. Horizontal is more than vertical by a factor of 10. But when you calculate the bulk anisotropy, okay, the gap between the shapes of these two curves is 2 to 3 orders of magnitude, can be, depending on what p-value you're using, it can be 2 to 3 orders of magnitude. So in a model sense, the anisotropy of mixed material where you have clay lenses on sand, that anisotropy can naturally come into your model. And that's very important if you have a stratified system and if you are seeing some really high vertical head differences. How do you get those head differences? And the key to that is to get the right shape of these horizontal and vertical hydraulic conductivity distribution. All right, there are some additional features this tool provides. For example, if you have depth dependency of conductivity with depth, typically shallow formations will have higher conductivity for the same sand material, for example, and as you go deeper in the formation, there's consolidation, cementation, compaction, and typically for the same grain material, coarse grain, your conductivity will decrease. And so this tool provides that flexibility to accommodate the depth dependency of those parameters. The other aspect the tool does is, for example, you can have pilot points for large-scale heterogeneity. The figure we are seeing here is that of Sacramento Valley. It's a really large system. We'll see some more details on the next slide, but the main point here is for large-scale heterogeneity, clays everywhere are not the same. Sands everywhere are not the same. So even if you're saying 100% sand, 100% sand on one side of the valley, for example, this is the Sierra Nevadas versus this is the coastal range, the meaning of sand could be different. And to accommodate that large-scale heterogeneity, this tool can accommodate that heterogeneity using pilot points. Okay. The second thing is depending on the depositional environment, if it's a stream and floodplain deposits, they may have a different character versus alluvial fan deposits may have different character. So that can be built in using zones and pilot points. So there's some flexibility you can use in the tool to refine the model, to inform some ground truth and bring that into the model with very few parameters. And that's the advantage of using texture-based aquifer parameterization. All right, so let's look at one example application in California we did a couple of years back, and one of the reports came out just early this year. It's a model called Sacramento Valley Model, SVSIM. It's a large valley, more than 7,000 square miles. There are over 4,000 well and boring logs. As you can see, it's really nicely, densely populated with a lot of well logs, great information, but how do you bring that information in a model? And the motivation for developing this tool was specifically to incorporate the texture data into the model in a seamless way. What's interesting is, look at the density of these boring logs, okay? And there's a point I want to make in one of the later slides about density and model performance, density of these well logs and model performance. Okay, so we saw model calibration. That's a completely different talk. Here, our focus right now is only to look at how we incorporated aquifer parameters in the model. The calibration looks as good as it does, but the main point here I'm trying to make in context of aquifer parameters is we took great care in not overfitting the model. Typically, if your water budgets are off, or if you're doing modeling calibration, most of the error is kind of dumped either in aquifer parameters, because those are the ones you tweak and you adjust, and if anything is off, it's taken up by aquifer parameters, okay? But that's something specifically we avoided. We said, okay, let's not overfit. There was good understanding of what the aquifer parameters should be based on prior studies and the experts that were involved in the advising us on what parameters make sense. So we always kept those parameters within plausible range and then avoid overfitting. But once we did that, that gave us a lot of control on how much water is flowing through the system, one, and how much storage capacity the aquifer has. So those two are important and often underrated or undervalued and underutilized information. Earlier, I think Philip presented comparing transmissivity values in his model, and that I was very encouraged to see that is being utilized. So that's great. So we did the same thing in Sacramento Valley model. Another nice aspect of using these well logs is heterogeneity comes in naturally using well logs. So once we use well logs, and each well log has its own set of percent coarse, percent fine values, once you integrate that on a model scale, the heterogeneity easily comes in. That's how the well logs inform the model. So that's a great aspect of this tool. And the final point I want to make for the SVSIM model is, when we plot this, on the y-axis is the model error as RMSE, okay, root mean squared error. On the right, or the x-axis, is number of well and boring logs within a 10-mile radius of that observation well. And what was encouraging to find out was that, hey, where you have a lot of well logs to inform aquifer parameters, that's where we saw the least error in the model. And that was quite satisfying to see that, okay, as you build or as you collect more information on the ground, that's going to feed back in the model and improve its performance. So that was the main message from this plot. Similar application in Arizona. This model, Phoenix AMA model, was released in June this year, very recent, and similar, large area. Well logs in this case were sparse, not as densely. I think we got spoiled with really good quality data that we got in Sacramento Valley, and we were expecting to see that everywhere. But, reality hit us and we said, dang, okay, we'll have to work with what we have, and that's fine. But there was enough for us to use that information, and we filled the gaps using data gap techniques, and we just filled those gaps for now with the promise that, okay, once the areas where we don't have well logs, once those become available, those can be easily integrated in this workflow. So that worked out pretty well. Well logs were sparse, but on the flip side, they had a great set of aquifer test data available. And so that was very encouraging. They had like 325 aquifer test results spread out in the model, which was great information to use. So even before we started any modeling runs, we had the model, so we have a grid to work with. Even before we start using the model or running the model at all, we had a model independent calibration target in the form of aquifer tests that are out there. So, we ran, and the natural heterogeneity that came from the logs, aquifer test parameters, we matched the hydraulic conductivity, and okay, yes, there was some tweaking to be done, some calibration to be done to fill in some of these gaps. But once we did that, we got a good distribution over 2 orders of magnitude for hydraulic conductivity distribution. We matched the mean and the overall distribution between the observed aquifer test results and the simulated test results at the same point where the aquifer tests were done was quite encouraging. So we got model independent calibration targets. This helped us constrain, again, good aquifer parameters. What should the values look like so that the water budget then gets controlled, not just by your head target, stream flow, stream downward interaction, all the good other. Again, I'm not saying this replaces it all. This is just one piece of that overall puzzle, right? Everything needs to come together and make sense. So this is just, we are just discussing aquifer parameters in this talk. Improves water budget estimates, and again, provision for future improvement. As new well logs become available, we can easily integrate that in the next phase of modeling. All right, let's looking at the examples. What are we doing now with this tool? Right now, we are, again, working for California Department of Water Resources. We are accommodating airborne electromagnetic surveys. But as we are doing that, and from our past experience, we realize that clay is hard to parameterize, and clays are interesting texture information. So that's where we thought, okay, we need to experiment with this binary system we are working with of all sand or all, cobbles or gravel or all clay may not be sufficient. There were some cases where we were struggling and we said, maybe, if we had 3 categories, that would be great. And so just as an improvement, we've included multiple textures right now. We will experiment and see what works, because, okay, more model parameters typically means an improved calibration, but how do you justify the values that you put in those values? It's more knobs to turn, so it's great, helps with the calibration, but you need to justify and somehow make sure it makes sense, right? So anyway, we are experimenting with that. So that's one of the changes we are doing. But the more important part is accommodating the resistivity data that we are getting from airborne electromagnetic surveys that California has conducted statewide surveys, and they've flown a helicopter with this equipment hanging down. It passes the signal into the aquifer from the transmitter, and then the response is recorded. Based on how the response is, there's some math involved in the background that can then interpret that aquifer property and change that into a resistivity number that comes out. Okay, so you have a resistivity number. What do you do with it? So that's where this tool, and I'll go over briefly on how we calculate or take this resistivity number and convert that to an aquifer parameter. So how do you do it? The AEM is airborne electromagnetic surveys. AEM data, what it gets released is measured in resistivity ohm meter numbers. Okay, and then what you can do is you can correlate some of these resistivity numbers and put some distribution around a mean and standard deviation and say that, okay, this range of resistivity value can be interpreted as clay, and then the next range is silty clay, and so on. So you can have multiple lithology information and correlate this with those numbers, right? Okay, so that's great. In the end, this is what the geophysical logs look like and the distribution in the ground. How do you do it? There are several assimilation methods we have tried. We've tried co-kriging, external drift, multiple indicator kriging, all of that good stuff. So far, we've got good success with co-kriging. The way it works is we use the well log lithology data as hard data because that's what you've measured in the ground. You exactly know what percent coarse, what percent fine. Great. But then AEM, although the resistivity numbers don't really directly translate to a hydraulic conductivity number, for example, but what it provides you is the distribution or the highs and lows. Where are the highs? Where are the lows? At least it gives you a relative distribution on the ground. And that's what you can interpolate. Use that as a soft data, as the co-kriging term. Use lithology as the hard main kriging term and co-krig this to get aquifer parameters, the same way, the same math as we saw earlier. So all that is good. We are doing some more refinement on how to do local search and kriging strategies, and then multiple, more texture, bring that into the equation. And again, we don't have to rigidly adhere to these relations, but those provide a guide to interpolating some of the log and fill in some of the data gaps that the logs have. With that, I'll pass it on to Rohit, who will present relevance in Texas.
Right, thanks, Vivek. Yeah, I won't take much of the time. I think we're very close to beer time. So, applications in Texas. So the biggest questions are, we have all this data available, but which kind, and how do we use that? Now, Texas has probably done a very good job, and thanks to TWDB and their staff on what they do and how they do it, and also the funding that they have available from the ledge. But a lot of this stuff, like the BRAX group, they collect a lot of these geophysical logs, and we have all these locations, and they've done stratigraphic interpretations. So we have a lot of this well log data available. And that's primarily like the first part of what you saw Vivek speak about. But the other part is also the GAM team and a lot of the bell logs that are available through the GAM team. And some of them, and some of the newer models that are coming through, they do calculate percent fines. And in most of the newer stuff that we are seeing, they are calculating percent fine, percent coarse. And sometimes that is used in a sort of texture-to-par light way in looking at or interpreting aquifer parameters, but we could do a better job. We're bringing in these tools, we can do a better job of quantifying that and translating that into our aquifer properties. It's just we have all this data, let's now use it in a better sense. Another one, and this is for the last part where he was talking about aquifer test data in Arizona and how it helped a lot where we didn't have well log information. And so this is sort of a plug for one of the projects that we're doing now for Texas Water Development Board. So thank you for them for the funding. And hopefully everyone here should have received an email from some entity. And so shout out goes to all the entities who've helped us. Of course, the TWDB staff, it's their project. But TDLR, who sent out an email blast on this project. And of course, TAG-D and Texas Groundwater Association. But really, we are looking for a lot of aquifer test data. And the more data that we have, it's better. And Vivek and SSP are leading this. I'm part of that team, and also H2O Geo Solutions. And we're creating this Aquifer test database that will, again, as Vivek said, it's going to be this statewide database, and it's going to help you better, make better models. Whoever is making those models, you're hiring a consultant, or TWDB is making those models, or maybe you have some local scale groundwater district wanting to make models. And so again, we have some responses from some parts of Texas, but any more data is again, we can utilize that and put that into the database. Some applicability to groundwater management as how we do that in Texas. So, we have 9 major, 22 minor aquifers. There have to be GAMs made for all these, but also there's GCD management models now coming through, the local models, and there were talks about that at this particular conference on these local models. And we're seeing more and more of those come through. And we can use these tools now that are available. So let's say you have a 3D stratigraphic model, and a lot of GCDs have that. You've used some tools like Leapfrog or Kingdom or some of the other tools where you've done your stratigraphy, you've done really nice analysis, and you really fine, maybe up to a foot level discretization on your layering on sands and clays. But how does that translate numerically to a model? How can you use that data to make a better model parameterization? I think that's where these tools come in. And it's not just those well logs, but it's also that Aquifer test database. It's also, hopefully in the future, we'll see more of AEM being used in Texas, especially in alluvium basin kind of aquifers, where it can be very powerful. And hopefully, all that goes into either a GAM or a local GCD model, and then help us better make better decisions on groundwater management. So one of the other potential applications, and we kind of were looking at it. So this is another TWDB-sponsored project, and we had this aquifer recharge site assessment being done. But again, the scale was like 90 square mile grids. I think Half and Intera did this project for, and some other team members did this project for TWDB. But you're really are looking at 90 square miles. It's very bird's eye view. You want to go to a really local scale and look at what's a potential site to create like a managed aquifer recharge project. If you're using stormwater or some other excess water, what are potential sites? And that's where a lot of this data, when it comes in, you can parameterize it better and create a better model. So this is one of the projects I worked on for TWDB in a past life. And we did this potential recharge estimation for all of Central and West Texas aquifers. And we're using a hydrological model for that. But we went up to HRU scale, which is less than 0.1 square miles. And you can see the disparity of recharge. So green is better, that's more recharge. I know you can't read the numbers. Red is pretty much no recharge. So you can see how with more data, we can make better models and look at these potential sites. So there's this myriad application for having this data and using the science to create better informed models and decision making. So again, the take home message is more data is better, but how do we utilize this? We improve conceptual models, we refine numerical models, and don't ask me any questions. Vivek is gonna take you home.
Well, just to summarize this whole talk, aquifer data is currently underutilized, in my opinion, and it needs to be part of the equation in model development calibration for sure. Texture2Par is a tool that was developed with the motivation to fill that gap. It reads percent coarse, percent fine from well logs. It can accommodate geophysical data from airborne electromagnetic surveys. And it provides natural heterogeneity. And you can be parsimonious in your parameters. You can have just a handful of parameters, but you can still get the heterogeneity on a basin-wide or regional scale and calibrate with very few parameters. And it's tethered to geologic conditions on ground. Aquifer test data is great because that provides a model-independent means of calibration, at least to get you started, to narrow down the predictive uncertainty, to improve your predictive capabilities of the model once you have reliable and more meaningful parameters in the model. So the take-home message is understand your aquifer. Here's our contact information. Feel free to reach out, write email if you have any questions. Happy to answer any questions.